Now let us do this result, which is again very important. So let x1, x2, xk be independent random variables with xi having normal mu I and sigma I square distribution. Let a1, a2, ak be real constants such that summation I is equal to 1 to k I square is greater than 0. Then summation xi, ai xi has normal ai mu I and summation I is equal to 1 to k I sigma I square. So that means linear combination of normal is again, linear combination of independent normals is again normal. Now once it is normal, I know its parameters are its mean and variance. So the first parameter mean would be nothing but ai times mean of xi, which is ai mu I. What would be the variance of summation ai xi? Because they are independent, it should be same as variance of ai square, summation variance of ai square variance of xi, which is this quantity. Now we also know that if x is normal mu sigma square, then xi minus mu I by sigma I is normal 0, 1. So its square would be chi square 1. And since xi's are independent, their squares would be independent. So by reproductive property of chi square, this will have a chi square k distribution. So let's try to do this. Let us see y is equal to summation ai xi. Then myt is expected value of e to power t summation I is equal to 1 to k ai xi, which is same as expected value of product I is equal to 1 to k e to power t ai xi. Since xi's are independent, so expected value of product would be same as product of expected value of e to power t ai xi, which is product I is equal to 1 to k. This is nothing but movement density function of xi at the point ti, which is summation I is equal to 1 to k. Xi is normal mu I sigma I square. So its movement density function would be e to power mu I times argument. Argument is nothing but ait, so that is why it becomes ai mu it, plus sigma I square, argument square, which is t square ai square by 2. So if you do it, it becomes e to power summation I is equal to 1 to k ai mu I t plus summation I is equal to 1 to k ai square sigma square t square by 2. Now this is nothing but mgf of normal with mean as summation ai mu I and variance as summation ai square sigma I square, which is the mgf of this. So by uniqueness of mgf, I can say that the distribution of y, which is summation ai xi, so y is equal to summation ai xi, has normal with these parameters. Now let us define zi as xi minus mu I by sigma. Then I know that xi minus mu I by sigma is normal 0, 1. So that means z1, z2, zk are normal 0, 1. Now since xi's are independent, and I know that functions of independent random variables are independent, so z1, z2, zk are IID normal 0, 1 random variables. So z1 square, z2 square, and zk square would be IID chi square 1 random variables. So summation I is equal to 1 to k zi square by reproductive property of chi square would be chi square k distribution. Now let's do this last result, which is again very useful. Let x1, x2, xn be a random sample from normal mu sigma square distribution. Let x bar is 1 upon n summation ai summation xi, so which is the sample mean. S square is 1 upon n minus 1 summation xi minus x bar whole square, which we call as a sample variance. Exactly. Then x bar would be normal mu sigma square by n. Not only that, the sample mean and the sample variance are independent. Not only that, n minus 1 s square by sigma square will have a chi square or n minus 1 degrees of freedom. Then expected value of x square would be same as sigma square, and variance of s square would be same as 2 sigma 4 n minus 1. Actually, this result holds for general distributions, as I'll give one of the problems. Now this result x bar is a linear combination of xi's with each ai as 1 by n. So by last result, this would be normal. So first follows from the last result. Now let us see x bar and xi minus x bar are independent. For that, let us define yi to be xi minus x bar and y as y1, y2, yn. So what I'll show is y1, y2, yn and x bar are independent. If I can show that y1, y2, yn and x bar are independent, then any function of y1, y2, yn and x bar would be independent. And your s square is nothing but a function of y1, y2, yn, and that would prove the result. So let's define yi to be this. Then summation yi turns out to be summation xi minus x bar, which is summation xi minus nx bar is 0. So this holds for general distribution, general random variables, or general variables that sum of deviations of observations from their mean is always 0. N minus 1 s square is summation xi minus x bar whole square, which is summation yi square. So I consider the joint MGF of y and x bar, and by considering that, I'll prove that y and x bar are independent. So my x bar uv is same as expected value of summation I is equal to 1 to n ui yi plus v x bar for u is equal to 1 to n and v belonging to R. So let us consider summation ui and summation ui vi plus vx bar, which is same as summation ui xi minus x bar plus vx bar, which is same as summation uj xj, which is this term, plus summation plus v times minus summation uj divided by n x bar. X bar is nothing but this quantity. So I combine this, so this becomes summation j is equal to 1 to n uj minus u bar plus v by n xj, which is same as summation j is equal to 1 to n tj xj. So where u bar is nothing but 1 upon n summation ui, tj is nothing but uj minus u bar plus v by n. Now note that summation I is equal to 1 to n ui minus u bar is some of the deviations of observations from mean, so this has to be 0. So therefore, summation j is equal to 1 to n tj, which is summation j is equal to 1 to n uj minus u bar plus v by n. But summation j is equal to 1 to n uj minus u bar is 0. So that means v by n added n times, so that becomes v. Summation j is equal to 1 to n tj square is summation j is equal to 1 to n uj minus u bar plus v by n whole square, which is same as summation j is equal to 1 to n uj minus u bar whole square, plus cross product term which would be plus 2 v by n summation uj minus u bar. But summation uj minus u bar is 0, so cross product would be 0. Then plus v square upon n square added n times, so that gives v square by n. So now I look at my x bar uv, which is expected value of summation I is equal to 1 to n ui yi plus vx bar, which is expected value of summation j is equal to 1 to n tj xj, which is same as, because xj's are independent, so it is same as product j is equal to 1 to n mxj tj. But xj is normal mu j sigma j square, normal mu j sigma square, so this is same as e to power mu tj plus sigma square tj square by 2. So this product gets converted into summations over the exponent. So e to power mu summation j is equal to 1 to n tj plus sigma square by 2 summation tj square. Now I put the values of summation tj and summation tj square, so I get this quantity. So one thing from here is clear that terms of ui's and vi's can be separated out. So it looks like ui, it looks like y and x bar are independent. So myy is same as my x bar u, and I put v is equal to 0. You put v is equal to 0, so you get this quantity. So that is the movement generating function of y. What is the movement generating function of x bar? So in the joint movement generating function, I put the argument of y as 0. Argument of y is u, so I put all u to be 0. So then you get e to power mu v plus sigma square v square by 2n. So clearly, my x bar uv, which is joint MGF, is same as the product of marginals for every u and v. So this implies that y, which is x1 minus x bar, xn minus x bar, and x bar are independent. So that means any function of this would be independent of any function of this. In particular, summation I is equal to 1 to n xi minus x bar whole square and x bar are independent. But s square is nothing but a function of this, so that means s square and x bar are independent. So that proves that s square and x bar are independent. X bar has a normal distribution. Now let's prove that n minus 1 s square by sigma square has chi square on n minus 1. So let zi is same as xi minus mu by sigma, z as root n x bar minus mu by sigma, y as n minus 1 s square by sigma square, which is same as summation xi minus x bar whole square by sigma square. Then z1, z2, zn are ID normal 0, 1. And we know that x bar is normal with mean of x bar is mu, variance of x bar is sigma square by n. Is sigma square by n. So I normalize it, x bar minus mu divided by standard deviation, which is sigma by root n, is normal 0, 1. So that means z would be normal 0, 1. So let w, which is z square, which is n times x bar minus mu whole square by sigma square, which is a square of a normal 0, 1 distribution. So w would have a chi-square on 1 degrees of freedom. And suppose t is summation I is equal to 1 to n zi square. Since zi is xi minus mu by sigma, so zi square would be square of a normal 0, 1, which is chi-square on 1. And since zi's are independent, so t would have, by reproductive property of chi-square distribution, as chi-square on n. So t is same as summation I is equal to 1 to n zi square, which is same as summation I is equal to 1 to n xi minus mu by sigma whole square. I add and subtract x bar over here. Then this becomes summation I is equal to 1 to n xi minus x bar whole square by sigma square. Cross product term would be twice times x bar minus mu, summation xi minus x bar. But summation xi minus x bar turns out to be 0. So cross product term would be 0. Plus x bar minus mu whole square added n times, so n times x bar minus mu whole square divided by sigma square. Now this quantity is nothing but y plus w. But we know that these are function of yi's and these are function of x bar, so these two are independent. So that means y and w are independent. So by 2, y and w are independently distributed. Thus, the moment density function of t would be same as the moment density function of y plus w, but y plus w are independent. So moment density function of y plus w would be nothing but product of their moment density functions, which is myt into mwt. But t, I know, is chi-square on n, so its moment density function is 1 minus 2t to power minus n by 2, because we have seen that t is chi-square on n. Is same as myt, and w we have seen is chi-square on 1, so its moment density function would be equal to 1 minus 2t to power minus half. So from here myt turns out to be 1 minus 2t to power minus n minus 1 by 2. But this is nothing but mgf of chi-square on n minus 1 degrees of freedom. So that means your y has chi-square on n minus 1 degrees of freedom, which is nothing but n minus 1 s square by sigma square. And I know that chi-square, for chi-square random variable, its expected value is same as degrees of freedom. So expected value of n minus 1 s square by sigma square is same as expected value of chi-square on n minus 1, which is same as n minus 1. So this gives me expected value of s square as sigma square. We also know that y square, variance of chi-square is nothing but 2 times degrees of freedom. So variance of n minus 1 s square by sigma square is same as 2 times n minus 1. So variance of c times x is same as c square variance of x. So that means n minus 1 whole square by sigma 4 variance of s square turns out to be 2 times n minus 1, which gives me variance of s square as 2 divided by n minus 1 sigma to the power 4. Now let me give this take-home problem. This characterizes the uniform distribution. So let alpha is less than beta, and let x be an absolutely continuous random variable, such that the whole weight of x is concentrated on the interval alpha beta. So that means probability x greater than or equal to alpha, less than or equal to beta is 1. So that x has uniform alpha beta if and only if probability x belonging to I is same as probability x belonging to j for any pair of intervals ij in AB having the same length. So that means probability that x takes value in an interval depends only on the length of the interval if and only if the x has uniform distribution. Let me give another exercise. So let x1, x2 be a random sample. That means they are IID from a distribution having finite mean mu and finite variance sigma square. Let x bar is the sample mean, which is 1 upon n summation I is equal to 1 to n xi, and s square is the sample variance, so 1 upon n minus 1 summation I is equal to 1 to n xi minus x bar whole square. Then you have to show that irrespective of what the parent distribution is, whether it is discrete, continuous, the expected value of sample mean would always be same as the population mean, which is mu, and variance of x bar is always same as sigma square by n, and expected value of sample variance is always same as the population variance sigma square. So take this as an exercise for any parent distribution. So here nothing is assumed about the distribution of x1, x2, xn, neither that they are discrete or continuous. So that was all about this module 29. Thank you for your patience, and have a great day.